All right, so these two problems just deal with drawing free body diagrams mainly and trying to understand what forces are acting on them. We can learn all kinds of things from these questions, but mainly the task is drawing the free body diagram. So this says when a constant horizontal force of 3 newtons is applied to a 1 kilogram block. So I'm going to draw a block. It's 1 kilogram, so things that have mass have a force of gravity that is acting on them when they are on planet Earth, which this is. It says it's resting on a table. We're not drawing the table because this is a free body diagram, so we're setting it free from its surroundings. But because it's on a table, it's resting on a table, that means the table has to be pushing back up. And that kind of a force is called a normal force. And we know that the normal force is equal to the force of gravity in this case, okay, because those are the only two forces that have upward components. If you were pulling up on this block with a rope or pushing down on it, the normal force would not equal the force of gravity. It's a really common misconception, so just note that this is the case if there's not a force being pulled up, which there's not. Okay, constant horizontal force of 3 newtons, and you can say that's force applied, for example. And do we know anything else? Like, well, it doesn't say anything about friction, okay, but it does say it's moving with a constant velocity, and that's a very important statement. If it's moving with a constant velocity, what do we know? The net force is equal to mass times acceleration. Well, if it's a constant velocity, that means that the acceleration is 0, which means the net force in that direction has to be 0. Well, right now it's 3, because we only have one force with 3 newtons pointing to the right. So we now know there must be another force pointing in this direction that is also 3 newtons, which is most likely the force of friction. So we have put the directions of all these forces. We know that the applied force is equal to the force of friction. They're both 3 newtons. Okay, well now, magnitude, we want to also list what is the magnitude of both of these forces. 1 kilogram block, that means the force of gravity is mg, right? So on Earth, that's 9.8 times 1, or 9.8 newtons. My arrows are not drawn to scale. 9.8 is bigger than 3, but we'll get over that. And the normal force then is also 9.8 newtons. So we've got the magnitude, we've got the directions. Next up, number 3, same situation. We want to draw a diagram, label all the forces, and label the magnitude of those forces if we can. Ooh, big thunder outside here. So there is a vertical wall, and there's a box against that wall, and we're pushing into that box with 80 newtons of force to hold it in place. Okay. So this is not a free body diagram. Now it's free. Okay, so I have a force going this way that is 80 newtons. Okay. Well, is it accelerating that way? No. Now this is applied force. So what is causing it or keeping it from accelerating the wall? It's a surface that is exerting a normal force. Okay, and you're like, well, normal forces point up. Yes, from the surface. So if the box is here, the ground points up. If the box is over here, the normal force points to the right. So we've got a normal force, and we know that that normal force is equal to 80 newtons as well, because it is not, there's no other forces in the left and right direction, and it has to offset the applied force to keep it from accelerating to the left. All right, well, what else do we know? Well, things that are on Earth and have mass also have forces of gravity on them. So in that case, this case, it would be 4 times 9.8, the mass times 9.8, and that is 39.2 newtons, pointing downward. Okay, well, stationary. the way I've got my free body diagram drawn right now, it's not stationary. It would be accelerated because we have unbalanced forces. So there has to be a balancing force pointing this direction to keep it stationary. So the magnitude of that force is 39.2 newtons. And what do you think is causing that force? Friction. Now, another thing that's interesting that we could find is the coefficient of friction. If we assume that this thing was just about to slip, that we had pushed just hard enough to keep it from sliding, then we could say the force of friction is equal to a coefficient of friction times the normal force. So if I wanted the coefficient, I could do the force of friction divided by the normal force, 39.2 over 80. So we could actually figure out what the coefficient of friction is if we knew that this was about to slip, and that would be a static friction force because it's not moving. And this would be actually the minimum coefficient of friction that would keep this from moving, because we have to offset gravity. We are only applying an 80 Newton force to the left, and so anything less than this thing is going to slide down the wall. All right, so that's that, 2 and 3. Just drawing some diagrams. Make sure that you know and understand when something is stationary or has a constant velocity, you know the forces have to be all balanced. Okay? If it's not constant velocity or stationary, if it's accelerating, then the forces have to be unbalanced.